now I'm going to say a few more words about the product topology. So I prepared a few simple examples to go through. My first example is just about the real line. So consider the real line with the standard topology, and the standard topology can be defined by the basis consisting of all open intervals from A to B, right? So this means that this is, as I said, it's the real line, and its topology is defined by the basis consisting of all intervals AB. Now, we're going to take another copy of the same thing, so it's going to be another real line with, say, intervals CD, just to distinguish from AB. But it is the same topology, so it's also this, the real line with the standard topology. So what is the product topology? So by definition, the product topology is going to be the set of all pairs X, Y, where X belongs to R and Y belongs to R. But this is, of course, just R2. So what is the topology on R2? So the topology, the product topology, tells us that the basis of this topology is going to be the set of all products of intervals. So it's all products of intervals, like A, B cross C, D. So in other words, the product topology on R2 is the topology whose basis is the set of all open rectangles, A, B, and C, D. And in the lecture we saw that this is the same as the standard topology. So the standard topology is defined to be the topology whose basis is the set of all open disks. So here we have open rectangles. It is a different basis, but it is still the same standard topology. So different basis, of standard topology. But the important thing about the product topology is it is just a way to introduce a natural topology on the Cartesian product of two topological spaces. So, and it's not going to go against your intuition. So in all questions on product topology, the challenge here is not in topology, but rather to identify the product. So maybe I hope that a few examples are going to help you. So let me go through the second example. So in my second example, I'm going to again look at the annulus. So suppose that this is X, this is Y, this is 1, this is 2. And then I'm going to look at the annulus given by the inequality X squared plus Y squared is between 1 and 4. Right? So this is the set between the two circles of radius 1 and radius 2. Okay, so now if I have a point on this annulus, how can I specify a point in this annulus? I mean, of course, I can just give the coordinates x, y, but then the kind of when you think of the annulus, then it's going to be the set of points x, y satisfying certain extra conditions, which is probably not very convenient, right? So what you can always do, you can specify this point by its so you can draw a line through the origin to this point, then you can check this angle, say theta. And another thing that you have, you can specify the distance from this point to, say, the inner circle. And this distance is going to be, I don't know, say d. Right, so I'm going to, it's going to be specified by theta, which is the polar angle. And d, which is the distance to the inner circle. So in other words, d is nothing else but what? square root of x squared plus y squared minus 1. But my main point is that the pair x, y is in one-to-one correspondence with the pair theta and d. So what is theta? Theta is the angle. So in other words, all possible values of theta, so they are, I don't know, all possible angles, so they're numbers after addition with 2 pi. So all possible, so it means that theta actually belongs to a circle, and d belongs to the interval from 0 to 1. So in other words, every point of this annulus corresponds to a pair where the first entry is a point on the circle and the second entry is a point on the unit interval. So which means that this annulus is actually the circle product with the unit interval from 0 to 1. Okay, so now slightly more complicated example. So let's look at the torus, and let's look at the torus of revolution in the 3D space. So let me first draw the torus, let's say, in orange. So this is going to be my torus, and then these are going to be my coordinate axes. Let's say the origin is going to be somewhere here. So this is going to be x, y, z. Alright, so now how can we specify a point on the torus? So suppose that on this torus I have some point, I don't know, let's say I'm going to call it whatever, say a point P on the torus. So T is my torus and it sits in the 3D space. Is the torus of revolution. You probably learned how to parameterize the torus of revolution in calculus 3, but in any case, yeah, it's not important now. So the important part here is that how can we specify the point P? So then what we can always do, this point P, it belongs to this circle. So imagine that you have a plane that passes through P and through the origin, and the plane is exactly vertical, right? So the plane that contains the whole z-axis, so if we rotate it, then at some point it's going to pass through P. And then consider the circle that is the circle of intersection of that plane with the torus. Alright? So then, inside this circle, we're going to have its center, and then we can join this center to the origin. And then here we have our angle. The center of that circle, it sits on the plane xy, so which means that it has polar coordinates, and the first of them is going to be the polar angle, say, I don't know, theta. But then, if you just look at this circle, so maybe, yeah, I think it's alright. So then we can draw this line from the center of the circle to our P and take the polar angle, so the angle between the horizontal line that goes, if you say this is 0, maybe, no, okay, 0 is this is, the origin is going to be O, and this is going to be, say, I don't know, if our point is P, then this is going to be, say, I don't know, O prime. So then we are going to take the angle from O to O prime and to P. So the angle from O prime, P is going to be, say, I don't know, psi. And the angle from the x-axis to O and then to O prime, x or prime is going to be theta. So then a general, well, a point on the torus is in one-to-one correspondence with the pair theta and psi. Right? So if I have two angles, then I can always first can take the point in the plane xy corresponding to the first polar angle, right? So then I'm going to take the plane that goes through this point, denoted O prime here, and the z-axis, and then I'm going to intersect my torus with that plane. So it's going to intersect it along this circle, and on this circle I'm going to take a point represented by the second angle, which is psi, and vice versa. If you have a point on the torus, then you can recover theta and psi. So it means that that points on the torus are described by pairs of angles. So in other words, since an angle is essentially the same thing as a point on the circle, S1 and S1, it means that a point on a torus is represented by 2 points on the circle. So it means that torus is the product of two circles. All right, and maybe one more example. So suppose that we have, say, Earth. This is Earth. And we have a satellite that flies around Earth on an orbit or whatever. So maybe it's not an orbit. Maybe it has some engines and they propel the satellite. So the question is, well, and suppose that I don't know. So the satellite is at some altitude, say h, and this altitude is less than, well, is of course bigger than or equal to 0. So it may be on the surface itself. So when it is about to be launched, it's going to be on the surface of Earth, and then it cannot go higher than a certain altitude, say a. So what is the possible set of positions of this satellite? Well, then, if you look at the satellite, then it is always above a certain place, a certain point on the surface of the Earth, right? So if this is a satellite, then if, say, we can denote by x, the corresponding point on the surface of the Earth that it is right above. Right, so it means that the position of the satellite, if the position is p, it can be described by the pair where the first entry is x, is a point on the surface of the Earth that the satellite is right above, and the second is h, is the height or the altitude, the height above the surface of the Earth of the satellite. So then x belongs to the sphere because it is on the surface of the Earth, and h is the interval from 0 to a, which is of course homeomorphic to the interval from 0 to 1. So it means that the set of all possible positions of the satellite is going to be the product of S2 for the point that the satellite is right above cross the interval. Strictly speaking from 0 to a, but all intervals are homeomorphic to each other, so it is from 0 to 1. Alright, so I hope it helps to understand the product better.